This is our fourth video on magnetism, and in this video we will continue practicing more questions related to magnetism, and we will also have some problems with coils and magnetic field created by the coils inside of the coils, the ones that we were determining with the right hand rule what direction the magnetic field is going to be inside of the coil in the previous video. In this one, we will determine how strong the magnetic field lines are and calculate the magnetic field lines. So let's continue with the problems related to the previous video where we were using right hand rule. In this question, we have positive charge in A, positive charge entering the magnetic field lines. I have to use the right hand rule to determine the direction of the force acting on the charge. Pause the video so you can check your answers, and after you unpause you will see the answer. So I have in this question the force acting on the charge is into the page. And for the next one, again, if I use the right hand rule to answer this question, I will have the force acting on this positive charge is to the left. The next question, you have a negative charge moving to the left and the magnetic field lines are into the page. So the force acting on this charge using the right hand rule is going to be up. In this question, they say that the charge of 610 to the negative 6 coulombs moves with a speed of 410 to the 5th meters per second through a magnetic field of strength 0.4. So this is the information that is given. So it's 0.4 Tesla, as shown in the figure on the right. What is the magnetic force experienced by the charge? So the force on the charge has the formula F is equal to QVB, and then you have sine theta. In this case, the angle between the magnetic field lines and the direction of the charge is 30 degrees. So if I plug in my numbers, I will have Q, which is 610 to the negative 6. The velocity is 410 to the 5th. And magnetic field lines is 0.4. And then I have sine of 30 degrees, which is 1/2. And that will give me the force of 0.48 newtons. In the next question, they say that the particle of negative charge, so there is a negative charge, is shot into a region that contains an electric field E, so there is electric field, crossed with a perpendicular magnetic field B, so there is also a magnetic field, so electric field, magnetic field. And if E is given 210 to the 4th newtons per coulomb and B is given 0.5 Tesla, what must be the speed of the particle if it is to cross this region without being deflected? So I have two plates. They have positive and the negative charge. The magnetic field lines are into the page. So this is the magnetic field line. This is a negative charge and it's shot straight, and we don't want it to be deflected. That means we want it to go all the way straight. And in order for that to happen, the magnetic field has to cancel the electric field lines. So the electric field lines will have to be acting. So let's look in which direction the magnetic field lines are acting. So if I use my right hand rule, and in order for that to happen, you have to have two forces acting on the charge. One is electric field force and the other one is magnetic field force that cancel each other. At first, let's figure out the direction of the force acting by the magnetic field lines. So if you have the negative charge directed to the way your thumb goes and your fingers away from you for the magnetic field, then the force acting on the charge by the, maybe I redraw the charge over here. So here is the negative charge, and the force acting on the charge by the magnetic field lines is going to be down. So here is the force. Then that means electric field lines have to be pointing up. The force by the electric field lines has to be pointing up. And for that reason, you have to have positively charged plate on the top and negatively charged plate at the bottom. And what you said here is the electric field line force must be equal to the magnetic field line force. So here is the electric field line force. Here is the magnetic field line force. And electric field line force is equal to Q times E. And magnetic field force is equal to QVB sine theta. And in this case, again, the charge is perpendicular, the movement of the charge is perpendicular to the magnetic field lines. So I can cancel the charge on both sides. The charge didn't even matter, and they didn't give you what the charge was equal to. They just said it's a negative charge. And then you can determine the velocity of the charge by solving for the velocity. So that's going to be E divided by B sine, and in this case it's 90 degrees, so it's E over B. We saw this formula before in the previous videos. So what we have, E is 2 10 to the 4th, and B is 0.5. So the velocity is equal to 4 10 to the 4th meters per second. So the particle needs to be moving at the velocity of 4 10 to the 4th meters per second in order for it to be able to pass through between two electrically charged plates and place in the magnetic field, the one that is given in the straight line. So here is another question that is given, and here they say that two singly ionized atoms, that means ionized, they're positively charged, move out of a slit at point S as shown and into the magnetic field of magnitude 0.1 Tesla pointing into the page. Each has a speed of 10 to the 6 meters per second. The nucleus of the first atom contains one proton and has a mass of 1.610 to the negative 27 kilogram, while the nucleus of the second atom contains a proton and a neutron and has twice as mass, which is 3.34 10 to the negative 27 kilogram, because proton and neutron have the same mass. And atoms with the same number of protons in the nucleus but different masses are called isotopes. So the two isotopes here are hydrogen and deuterium. Find their distance of separation when they strike a photographic plate P. So we need to calculate the radius of each, and from the radius we will know the diameter. And when we know the diameter of one and diameter of the other one, we can figure out how far apart they will land. So in both of these cases, I have the centripetal force. The centripetal force is equal to the magnetic field force. So I have mv squared over r is equal to, let's do r1, is equal to qvb, and sine theta, sine is going to be 90 degrees, so I'm just going to keep sine, take away sine for now. So r1 is equal to, and this is the mass of the first one, and the charge is the same for both of them because they're one has one proton and the other one neutron. One has only proton and the other one has proton and neutron, so both ionized atoms are having the same charge. So r1 is equal to, I can cancel one of the velocities from both sides, so I will have m1v divided by qb. And for the second one, we're gonna have m2v, and they have both the same velocity when they enter, divided by QV. So to find R1, I'm gonna plug in the numbers and I will get, so here I have calculations for R1, and for R2 I'll do the same thing. I will plug in their numbers, the mass, velocity, charge, and the magnetic field. So I get twice as big number because the mass is the only difference that they have. And diameter for the first one is 0.208 meters, and diameter of the second one is 0.416 meters. So the distance that they will land between them, so the distance that they ask you how far they will land away from each other, is 0.208 meters. In the next question, they say that two wires each having a weight per unit length of 1/10 to the negative 4 newtons per meter are parallel with one directly above the other. Assume that the wires carry currents that are equal in magnitude and in opposite direction. The wires are 0.1 meter apart, and the sum of the magnetic force and gravitational force on the upper wire is 0, so they cancel each other. Find the current in the wire. So I have one wire and I have another wire. The distance between them is given, so I have this distance given, 0.1 meter apart, and the currents are in opposite directions, so maybe this current in this direction and this current in this direction. The force that is acting on the upper wire are the force of gravity and the magnetic field force that keeps the wire from falling down. So what I have to set up here is the force of gravity must be equal to the magnetic field force to cancel each other. And the force of gravity is mg on the top wire, and the gravitational, the force between two wires, or wire acting on the other wire. If you remember from the previous videos, the magnetic field force between two wires is equal to mu divided by 2 pi, and then I have I1, I2, in our case it's the same I and I, divided by the distance between them, and times the length of those wires that are in contact. And we are given that, well, actually there's a trick in this question. I will show you the trick in a second, but let's look at this part. This is K, which is 210 to the negative 7. So I have to find the current. So what I have is M, I'm gonna divide it by L, both sides, and then I have G, and I'm gonna divide the G both sides by K, so your K is in yellow, so I'm just gonna divide by K, 210 to the negative 7, and then I'm gonna times both sides by D, and I will have I, and it's the same current in both directions. I1 times I2 will give me squared. And the trick in this question is that they give you weight per unit length. And so the weight per unit length is mg divided by L. So this number is given. So instead of mg divided by L, I don't have the mass and I don't have the length, but I know how much weight per length. So that is 1/10 to the negative 4. So this part is given. And then I have the distance between them is 0.1 meter, and the K is 210 to the negative 7, and that is equal to I squared. So if I solve for I is going to be equal to 7.07 amps. For the next question, they say that if the current in each wire in the problem above is doubled, how far apart should the wires be placed if the magnitudes of the gravitational and magnetic forces on the upper wire is still to be equal or cancelled? So if you double the currents, you will have 2I times 2I. So the new one is going to be 4 times as big as the 4I squared. So what I'm going to have on one side is 4 times I squared, and on the other side you still have the same weight per length. Your constant K is 2 10 to the negative 7 is still the same, and D needs to change. And in order for compensate the left side and the right side, you also have to make the other side 4 times as big. So you will have to change the distance 4 times as big. So if before the distance was 0.1 meter apart, now it will be new distance is 4 times as big, which is 0.4 meters apart. So under these conditions, so doubling the current will still keep the wire separated, with the top one not falling down and canceling its gravitational field. So we talked about the right-hand rule when we have a coil or solenoid, and if a long straight wire is bent into a coil of several closely placed loops, the resulting device is called a solenoid or electromagnet or a coil. So the field inside of the solenoid can be calculated by the formula that is provided. So you can calculate the magnetic field inside of the solenoid. We were talking about the right-hand rule and how to determine the direction of that magnetic field. So N is the number of turns per unit. So N, the lowercase n, is the number of turns per unit. And then mu is still magnetic permeability, and that is 4 pi 10 to the negative 7. The letter K will change that mu because mu in the vacuum it is 4 pi 10 to the negative 7, but in the different medium it's going to be a different number. So K is just the relative to the vacuum permeability, and then I is the current. So let's look at some questions where we can use the formula mu and I. Sometimes my students like to change this formula into call it mu as U and I. So if I'm calculating the magnetic field inside of the coil, they call it mu and I. Here's the first question related to the solenoid or the coil. A certain solenoid contains 100 turns of wire and has a length of 10 centimeters. Find the magnitude of the magnetic field inside of the solenoid when it carries the current of 0.1 amps. What is the momentum of a proton orbiting inside of the solenoid in the circle with a radius of 0.02 meters? The axis of the solenoid is perpendicular to the plane of the orbit. And approximately how much wire would be needed to build the solenoid? Assume that the solenoid has the radius of 5 centimeters. So the first one, I want to calculate the magnetic field inside. So the magnetic field inside is going to be mu and I, and mu is 4 pi 10 to the negative 7, and is the number of turns, and we have 100 turns per unit length, which is 10 centimeters, 0.1, and the current is 0.5. So I get the magnetic field is equal to 6.28 10 to the negative 4 Tesla. So for the second question, they ask you to find the momentum of the proton orbiting in a circle of the radius of 0.02 meters near the center of the solenoid. We can say that the force acting on the solenoid is on the proton is the magnetic field force. So I can say for B that the force is equal to the magnetic field force. So from here I can say that MA is equal to QVB, and it's circular motion, so it's AC. So I will get mv squared over r, we used this formula before, is equal to QVB, and mv is the momentum. So one of the v's cancel, what's left is mv, and they ask you about the momentum. So here is the momentum is equal to r qb. So if I plug in all my numbers, I will get that momentum is equal to 2.01 10 to the negative 24 kilogram meters per second. And for the last question, they say approximately how much wire would be needed to build this solenoid. So if I want to determine the length of the wire that is needed, I need the number of the turns times the circumference, which is 2 pi r. So each circumference and n is how many turns I have. So I have 100 turns, and each turn is the length of 2 pi, and the radius is given 0.05 meters. And that will give me 31.4 meters of wire I needed in order to be able to make this solenoid. Here's one question that I found in study guide for AP Physics 2. And a pair of long straight vertical parallel wires separated by a small distance of 0.5 meters. And the current of one is 8 amps and the other one is 4 amps directed downwards are established in the wires. Find the magnitude in the direction of the magnetic field between the wires at 0.1 meter from 4 amp wire. So if I have one wire, they're vertical wires, and I have another wire, and the distance between them is 0.5 meters, the currents in the wire are pointed down, and it is 8 amps and 4 amps. And they ask you to find the magnetic field 0.1 meter away from the from 4 amp wire. So I need to find where the yellow line is. So at first I'm gonna find the direction of the magnetic field. So the magnetic field is gonna be in this direction for each wire. So it's in this direction. That means on the right side of each wire the magnetic field is coming out, and on the left side of each wire the magnetic field is going down. I use the right hand rule to determine this part, and here's the picture of the right hand rule that I used to determine the direction of the magnetic field around the wire. So I can calculate the magnetic field for the first wire. It is mu sub 0 divided by 2 pi, and then I have I over the distance for the first wire. So I will get B for the first is equal to 2 10 to the negative 7, current is 8, and the distance is 0.4. So that will give me 4 10 to the negative 6 Tesla. And that one is directed toward me. And for the second one, with the 4 amps in it, I have 2 10 to the negative 7, but now if the current is 4, and divide by that distance, which is 0.1 only, and so that will give me 8 10 to the negative 6 Tesla. And the resultant one, so the resultant magnetic field at 0.1 meters away from 4 amps wire I will have the difference between them, which is, because one is pointing, the 8th one is pointing out of the page, and the 4 amps is pointing into the page. So the resultant is going to be the difference between them. So that is 4 10 to the negative 6 Teslas. And it is also into the page. I saw this question in the multiple choice questions, and so I thought that I would solve it with you. A particle with a charge is given, experiences a force of, and is given how much force, and is traveling through a 3 Tesla magnetic field at an angle of 30 degrees. What is the particle's velocity? So the force is given by QVB and sine theta. The force is given, which is 2 10 to the negative 12. The charge is given 6.4 10 to the negative 19. The velocity we are looking for, it's 3 Tesla magnetic field, and the angle sine 30, which is 1/2. So the velocity is equal to 2 times 10 to the 6 meters per second. We will stop our video on magnetism 4 with that question, and I will say thank you for watching this video, and I hope I see you in the next one.